Chapter 10, Number 61. After you pick up a spare, your bowling ball rolls without slipping back towards the ball rack with a linear speed of v1 of equal to 2.62 meters per second, as shown in the figure. To reach the rack, the ball rolls up a ramp that rises through a vertical height of h equals 0.47 meters. A. What is the linear speed of the ball when it reaches the top of the ramp? And B. If the radius of the ball were increased, would the speed found in A increase, decrease, or stay the same? And explain. So this is going to be relatively straightforward. This is an energy conservation problem. There are only conservative forces acting, because remember that during rolling without slipping, friction does no work, so it doesn't change the energy state. And so we can say that the energy at the start, at the bottom, is equal to the energy at the top. We will set our 0 point here. That's y equals 0. So our energy at the bottom is 1/2 mv1 squared, but also 1/2 I omega 1 squared. And that's going to have to equal 1/2 mv2 squared plus 1/2 I omega 2 squared plus the potential energy mgh. And then our next thing is to note, or to remember, or to look up that for a, we assume, actually it's interesting, they don't actually tell us what kind of ball it is. So my understanding of bowling balls is that they are solid, and so we have 2/5 mr squared for their moment of inertia. So we can clean up our equation a little bit. 1/2 mv1 squared plus, and let's put that in, and we get the half, but now we'll have 2/5 mr squared for I, and we also know that it is rolling without slipping, which tells us that v equals r omega, or omega can be written as v1 over r squared. And that's got to equal 1/2 mv2 squared plus 1/2, and the same sort of logic here, 2/5 mr squared and v2 over r quantity squared. And then we still have, tagging along, the gravitational mgh. That's kind of convenient because it puts everything in terms of m, so that's useful, right? We have m's here, and here, and here, and here, and here, and since there's an m in every term, we can divide it out, so it goes away. And so I have 1/2 v1 squared, and then I have 1/2 times 2/5, which is 1/5, and the m's gone away. And then I have something else really kind of interesting. I have an r square up here, and then I have an r quantity squared down there, and those are going to cancel. So then I'm just left with a v1 squared. And the same sort of thinking over here gives me 1/2 v2 squared, but again the r's are going to cancel, and I'll get 1/5 v2 squared plus mgh. Then we've got to do a little bit of fraction combination. 1/2 plus 1/5 is the same as 5/10 plus 2/10, so this is 7/10 v1 squared equals 7/10 v2 squared plus gh. And a bit of a glitch, I wrote in mgh, but it's just gh over there. And then we're solving for, if we go back here, we're looking basically for v2. So I would have 7/10 v2 squared equals 7/10 v1 squared minus gh. I'm going to go to the screen just to. So we cross multiply by 10/7, and we end up with v2 squared equals v1 squared minus 10/7 gh. And now we can just take square roots of both sides, and we're left with v2 is the square root of v1 squared minus 10/7 gh, which is all numbers we know. So it's 2.62 meters per second quantity squared minus 10/7 times 9.81 meters per second square times 0.47 meters. And it's the root of all that. 0.52695 meters per second, which, because we have at best 2 sig figs, is really 0.53 meters per second. And then part B. If the radius of the ball is increased, what happens to the speed? And the answer is nothing, because r dropped out. So as long as this thing could fit on the track, so we can follow the conditions as given, it doesn't matter if it's a pea or a beach ball, as long as the track still works the way it's supposed to be working. So there we go.